Welcome to another deep dive. Today we're going to be talking about the concept of a timeless universe.
Ooh, sounds fun.
Yeah, it's a very interesting topic. We'll be taking a look at Julian Barbour's book, The End of Time. And before we get started, be sure to hit that like button and subscribe to the channel so you can keep up with all of our mind-expanding deep dives.
It's a real head-scratcher, this one.
Yeah, it is. Physics, time, revolution. Sounds a little heavy.
I won't lie, it's a dense read, but it really gets you thinking about how we understand pretty much, well, everything, Like, what if time, the time that we all experience, is just an illusion?
Okay, wait, hold up. So you're telling me all those deadlines I'm stressing over, they aren't even real? See, I knew it.
Well, hold on, not quite. It's a bit more nuanced than that. But hey, that's what we're here to figure out, right?
Yeah.
Barbour's whole journey with this, it all started back in 1963. Imagine this. You've got this young, bright physicist just soaking up the words of, well, the legendary Paul Dirac. And Dirac is questioning, like, the very foundation of space and time.
Well, okay, so before we go any further, let's back up for a second. Paul Dirac, for those of us who, maybe didn't spend our college years in theoretical physics, can you give us a little refresher? Who is this guy?
Oh, absolutely. So Dirac, he's this brilliant physicist, like top tier. He did a ton of work in quantum mechanics, and he even predicted antimatter. The guy was a genius. But yeah, he was really struggling with these huge questions about space and time. And that's what got young Barbour hooked.
Okay, and so that fascination, it basically sent Barbour on this, lifelong quest to understand what time really is. But before we get lost in the weeds of, hardcore physics, tell me about this farmhouse.
Oh, right. So this is where things take a bit of an unexpected turn. Barbour decides to buy this historic farmhouse on a whim, and this, believe it or not, it kind of fuels his research.
All right, now I'm really curious. How does a farmhouse lead you to the physics of time? How are these things connected?
Well, living in a place so full of history, surrounded by all these reminders of the past, it got Barbour thinking, what is time, really? Is it this constant flow, like Heraclitus believed? Or is it this unchanging, static thing like Parmenides argued?
So two very different philosophers, two completely different views of time. What did Barbour think? Which side was he on?
He was more drawn to Parmenides' view, the idea of a timeless reality. And to really explore this, he starts with this super simple question. What exactly is an instant of time? How do we even define now?
That's a good question. I mean, we throw around the word now all the time, but do we ever really stop and think about what it actually means?
Exactly. Barbour argues that this idea we have of now, it's actually a trick our brains are playing on us. He compares it to a three-dimensional snapshot. Like, think about it. Right now, at this very second, you're experiencing all these sensations, sights, sounds, feelings. Barbour says our brains are taking all of that and weaving it into this single, unified now.
So it's like our brains are always taking these mental pictures and then stringing them together to make it seem like time is flowing.
Exactly. And Barbour even calls these snapshots time capsules. Our brains, with all our memories or experiences, they're like time capsules. And so are the layers of the earth, with all those fossils from the past. Everything we know about history, it's all contained in these present structures.
Whoa, okay. Mind blown. But if everything is just a bunch of these nows, then how do we explain all the motion and change we see around us? I mean, the world clearly isn't frozen in a single snapshot, right?
You're right, it's not frozen. And this is where Barbour gets even more interesting. He says our perception of motion, kind of like our perception of time, is also a creation of our brains.
Okay, so how would he explain something like gymnast, doing a backflip?
Mm-hmm.
That's definitely motion, right?
Picture this. You're watching that gymnast. Your brain isn't processing everything instantly. There's a tiny delay, and Barbour argues that this delay, along with the way our brains connect those snapshots together, that's what creates the illusion of this smooth, flowing motion.
So it's like watching a flip book, where each page is slightly different, and when you flip through them fast, it looks like movement.
Perfect analogy. But to really get Barbour's take on a timeless universe, we need to jump into this classic physics debate. Newton versus Leibniz.
The battle of the titans. Newton with his absolute space and time, and Leibniz who said it's all about relative motion. Let's get ready to rumble.
All right, so Newton, he believed that space and time were these absolutes, like a fixed, unchangeable grid where everything happens is like, a cosmic GPS.
Okay, so like a giant invisible map of the universe.
Exactly, but Leibniz wasn't having it. He said motion is relative, that it only makes sense to talk about things moving in relation to each other. No absolute frame of reference, no cosmic GPS.
Two brilliant minds. Two totally opposite views on space and time. So where does Barbour fit into all of this?
He's trying to bridge the gap between these two seemingly opposite ideas. And to do that, he introduces this wild concept called configuration space. He calls it triangle land.
Triangle land. Now I'm even more lost, but definitely intrigued. Break it down for me. What is this triangle land?
So picture three particles. They can form all these different triangles, right? Different shapes and sizes. Each point in triangle land is one possible arrangement of those three particles.
So it's like a map of all the ways they can be arranged. But we're talking about the entire universe here, right? Not just three particles.
Right, but stick with me. This is where it gets good. The shape of that triangle, it reflects its energy and its angular momentum. Just by looking at the shape, you can learn something about its physics. Now imagine doing that for every particle in the whole universe.
So you're saying triangle land becomes universe land, where each point is a different arrangement of every single particle.
Exactly. And this is how Barbour brings Newton and Leibniz together. Individual systems, like our triangles, can have energy and momentum, but the universe as a whole could actually have zero. And that means you don't need Newton's absolute space and time anymore. It's all about the relationships between things, just like Leibniz said.
Whoa, that is mind-blowing.
Yeah.
Okay, but we're talking about time not existing, right?
Yeah.
And we're doing this whole deep dive within the context of Einstein's theory of relativity, which is all about time. How does that even make sense?
It seems like a paradox, I know. But remember, relativity isn't about some mystical idea of time flowing. It's about how we measure time, using actual physical clocks, and how motion affects those measurements.
Right, like those light clocks we talked about before. Remember, the faster the clock moves, the slower time seems to pass.
Exactly. Relativity is about the practical stuff, how we measure time, not about some big philosophical concept of time itself.
So where do Barbour's nows fit in with all this, with Einstein's theory?
Well, he argues that both Newton and Einstein, they were focused on events points in space-time. But for Barbour, it's all about those three-dimensional snapshots, those nows. They're the fundamental building blocks. The question is, how do these individual nows come together to form the universe we experience?
All right, hit me with it. What's the next mind-blowing idea? How do you go from these snapshots to the whole vast universe?
That's where best matching comes in. It's a way to compare two different nows. You basically try to line them up as closely as possible and see what the difference is. Imagine trying to perfectly overlap two photographs that are almost, but not quite identical.
Okay, I need a visual. Give me an example.
Picture two islands. We'll call them Tristan and Isolde. They have similar shapes, but they're not exactly the same. To best match them, you'd try to align their coastlines so they overlap as much as possible, and whatever's left over, that's the intrinsic difference between them.
So you're basically looking for the best possible fit, like solving a cosmic jigsaw puzzle.
Exactly. And this brings us to the big dilemma. Is space-time this fundamental thing, like a canvas that already exists? Or is it something that emerges from the relationships between all these nows?
So it's like asking, is the universe a finished painting, or is it like a mosaic that's always changing?
That's a great way to put it. And to really dig into this question, we need to dive headfirst into the wacky world of quantum mechanics.
Oh boy, here we go. Quantum mechanics, always a wild ride. All right, everyone, let's take a moment to catch our breath and process all of this mind-bending stuff. My brain feels like it just did a backflip.
Okay, so are we ready? Deep breaths, everyone, because we are about to enter the quantum realm, and things are about to get really, really weird.
Here we go. Fasten your seatbelts, folks. Okay, can we just do a quick recap? What is quantum mechanics again?
Well, the simplest way to put it is it's like the physics of the really, really tiny stuff. You know, the subatomic world. And the biggest thing to remember is that in this world, things are fuzzy. It's not all neat and tidy. Instead of things having, a definite position and speed, it's all about probabilities and possibilities. It's like the universe is playing dice, and you don't know what the outcome is until you actually look.
Okay, so it's not like, those little electrons orbiting the nucleus all nice and neat, like planets around the sun.
Yeah.
It's more like this cloud of maybe it's here, maybe it's there.
You got it. And here's the crazy part. When you try to observe it, when you try to measure it, that actually seems to affect the outcome.
Okay, now that just breaks my brain every time. Didn't we talk about this before with that double slit experiment?
Yeah. That's a perfect example of how weird quantum mechanics is. You got this beam of particles, and you shoot them at a barrier with two slits. Now, if those particles were acting like, little marbles, you'd think you'd see two clumps of them on the screen behind the slits, right? But no,
You get this wave pattern, right? It's like those particles are somehow going through both slits at the same time. How is that even possible?
that's the million-dollar question. And the even weirder part, if you try to figure out which slit each particle is going through, like if you try to measure it, that interference pattern, it just disappears. Poof! It's like those little particles know you're watching them, and they suddenly decide to act like normal.
So does that mean reality is like undefined until we actually look at it? That's kind of amazing and a little bit scary if you ask me.
I know, it's a lot to wrap your head around. But so how does Barbour tie this quantum fuzziness into his idea of a timeless universe? Well, that's where the wave function comes in. In quantum mechanics, the wave function is this mathematical description of all the possible states a particle can be in.
So instead of saying, okay, this electron is here and it's moving at this speed, you've got this wave function thingy that's like, well, it could be here or here or here, and it could be moving at this speed or this speed or this speed. It's all those possibilities at once.
You got it. It's like a menu of all the possible options for that particle. And now, Barbour takes this even further. He says, what if the wave function doesn't just describe tiny particles? What if it describes the entire universe?
Wait, hold on. A wave function for the whole we universe? That has got to be one massive wave function.
It is. But stay with me here. Remember how Barbour says the universe could have zero total energy and momentum? Well, guess what? There's an equation in quantum mechanics for systems with zero energy. It's called the Wheeler-DeWitt equation.
Now, this equation, it describes like the whole shebang, the whole universe as one giant quantum system.
Ding, 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 you got it. And here's the kicker. The Wheeler-DeWitt equation, it doesn't have time in it. It's timeless.
Whoa, whoa, whoa. Back up a second.
Yeah.
So, if this equation is describing the universe and it's timeless, doesn't that mean the universe is timeless too? But wait, how does that even make sense? Things are changing all the time. Stars are born, galaxies evolve. I'm getting older by the minute.
I know, it's a big leap, right? But to understand it, Barbour looks at how atoms behave. You've got the stationary Schrödinger equation, right, that describes atoms in their stable, unchanging states.
Right, so like those specific energy levels that electrons can be in, those levels are fixed, right? They don't change.
Exactly. Those energy levels, they're kind of like those different nows in Barbour's picture. Each now is stable, like self-contained, but they're all linked together within this structure of the wave function.
So the universe is like this giant atom just hanging out in this state of perfect, timeless balance.
That's a good way to visualize it. It's not that the universe is frozen or anything. It's more like all the possibilities are kind of existing at once within this wave function.
Okay, my head is spinning. So everything is happening at once. How do we get this illusion of change and the flow of time? Why aren't we like experiencing all those possibilities simultaneously?
Remember those time capsules we talked about? Those are super important here. Barbour says that those connections within the wave function, the links between those different nows, they're what creates the appearance of things changing. It's like this echo of what came before.
So it's not actual motion. It's more like a relationship between those different nows.
Think of it like ripples in a pond. The water itself isn't flowing in a specific direction, but those ripples, they create a pattern that looks like movement, right? Barbour says maybe our experience of time is kind of like that. It's a pattern woven into a bigger static reality.
But even if time is an illusion, it sure feels real to me. We remember things from the past, we think about the future, and what about history? How does that fit in if everything's already out there in the wave function?
To explain how history happens in a timeless universe, Barbour uses this really cool analogy, the ionization track of an alpha particle. So you've got this tiny alpha particle zipping through a cloud chamber.
Oh yeah, I vaguely remember those from physics class. They leave a trail behind them, right? Like a tiny vapor trail?
Exactly. As that alpha particle zooms through, it ionizes the atoms in the chamber, leaving this trail of little bubbles. That trail, it's like a record of where the particle has been. And Barbour says that's kind of how history works. You need a specific sequence of events, you need low entropy, and you need something to record those events.
Hold up, what's low entropy?
Entropy is like a measure of disorder. Think about a perfect, untouched field of snow. It's got low entropy, it's very ordered, but if someone walks across it, now you've got a record, right? You've got their footprints, that's history.
Oh, I get it. So that alpha particle, it's like that person walking on the snow. It's leaving a trace, a history in that cloud chamber.
Exactly. And Barbour argues that the wave function itself, as it spreads through this giant configuration space, the space of all possibilities, it can actually find those time capsules, those low entropy structures that can record events, and it makes them more likely to happen.
So the wave function is kind of like, I don't know, a sculptor. It's shaping all these possibilities, making some outcomes more likely than others, and those are the outcomes that create history.
That's a really interesting way to think about it. It's almost like the wave function is trying to tell a story, trying to weave together all these timeless possibilities into something meaningful.
Okay, wow. My brain needs a break. So basically we're saying the universe is this giant quantum time capsule.
It's a wild idea, right? And it really makes you rethink what we even mean by time and reality. But what does it all mean for us?
Yeah.
For our lives, our choices? That's what we'll explore next.
All right, I got to say, my brain is officially fried. Like, we've gone deep into the physics of a timeless universe, but now I'm stuck on the philosophical side of things, you know. If everything is happening at once, all in this giant wave function, then what does that mean for free will? Like, do our choices even matter?
That's a great question. And it's where Barbour brings in this idea of resonance. It's fascinating. Think of it like this. Each of those nows, those configurations of the universe, they each have a unique, like, frequency, like a tuning fork.
Okay, so you're saying the universe is like a giant orchestra, and each now is playing its own note.
Exactly. And Barbour argues that our consciousness, our sense of self, it comes from the specific frequency we resonate with within this whole massive symphony of possibilities. It's not so much that we're making choices in the way we usually think about it, but rather that our very existence is kind of aligned with certain possibilities, and those are the ones we experience.
Okay, I think I'm starting to get it. It's like we're tuning into a specific channel on the cosmic radio, right? But if our existence is already, you know, set within this timeless structure, then what's the point of anything? Does life even have meaning if it's all just, like, predetermined?
Well, Barbour says meaning isn't something that's imposed on us from the outside. It's something we create through, through our interaction with the world, through that unique resonance of our existence within all those possibilities.
So instead of looking for meaning in some grand plan, we find it in the present moment, in how our frequency interacts with the music of the universe.
Precisely. And remember those time capsules. They're not just records of the past, they're also key to finding meaning in a timeless universe. Because when we create records, when we leave traces of our existence, we're adding to the overall resonance of the universe.
So it's not just that our lives have meaning because, you know, we experience things in our own unique way, but it's also because we, like, leave a mark, a unique vibration that affects the whole symphony. It's like each of us is adding our own melody to the cosmic song.
Exactly. And those melodies, those echoes of our being, they can even influence the resonance of other nows, other possibilities within the wave function. It's a pretty amazing thought.
It really is. But this whole concept of a timeless universe with everything existing at once, it's a bit scary, to be honest. What does it mean for, like, death?
That is a deep question, and Barbour doesn't have all the answers. But he does suggest that maybe in a timeless universe, death isn't the end, but a transition to a different kind of existence within all those possibilities.
So instead of just, you know, ceasing to exist, our consciousness could continue on in some form, like our melody keeps playing even after we're gone.
It's definitely a possibility. And this ties into one of Barbour's most beautiful analogies. He compares this timeless landscape to, like, a heavenly vault filled with artistic masterpieces.
Wait, artistic masterpieces. Tell me more about that.
Well, Barbour, he gets this idea from the poet Keats. Keats wrote about the timeless beauty of a Grecian urn. And Barbour suggests that each configuration of the universe, it's like a work of art. And this whole landscape of possibilities, it's like a collection of all those masterpieces existing together in their timeless splendor.
So now it's like frozen in time, but it still has this inherent beauty and meaning.
Right.
Like a sculpture or painting.
Exactly. And our experience of time, our journey through life, it's like we're wandering through this amazing gallery. We get to experience the beauty of each masterpiece one after another, and that creates this unique and meaningful story.
It's like watching a flower bloom in one of those time-lapse videos.
Sure.
You see the whole thing happen in just a few seconds. But each individual frame, each moment of that bloom, it's beautiful.
That's a great way to put it. It really shows how our idea of time shapes how we understand reality. We're so
Yeah.
used to experiencing things in a linear way that it's really hard to imagine this idea of a timeless reality where everything is happening at once.
It's like trying to describe colors to someone who's been blind their whole life.
Exactly. But even if we can't fully grasp this idea of a timeless reality, we can still catch these glimpses of its beauty and complexity. And those glimpses, they should inspire us to keep questioning and keep exploring.
Well, this whole conversation has been one giant glimpse for me. It's overwhelming, but it's also incredibly inspiring.
It really challenges us to rethink everything we thought we knew about time, reality, and the meaning of life.
And as we wrap up this deep dive into Julian Barbour's mind-blowing book,
Hmm.
I think the biggest takeaway for me is just this sense of awe and wonder. If everything is existing at once in this timeless world, then that makes every moment, every interaction, every choice incredibly precious.
It's a good reminder to really appreciate the present moment, to enjoy the symphony we're all a part of, and to add our own unique melody to the music.
Absolutely. So keep questioning, keep exploring, keep diving deep. And if you want to have your own mind-bending experience, check out Julian Barbour's book, The End of Time. It's a tough read, but I promise you it'll change the way you look at the universe and your place in it. Until next time, fellow knowledge seekers.